So hi everyone, we'll start in, I think, after 3 minutes. Just wait for a couple of minutes and I guess we can start. So I think we can start. It's already 3:05. So good afternoon, everyone. My name is Musa Rafiq. I'm the course TA for course Digital Circuits that is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. I am from IIT Kanpur. I'm a PhD student in the Department of Electrical Engineering. So we carry out this TA work every week from 3 p.m. to 5 p.m. as a part of our PMRF deliverables. So total there are 12 lectures scheduled, and this is lecture number 11, or should I call it a problem solving session. And other than that, we will have one extra session, which we call the recap session, that will be held, I think, on 20th of October, where we'll be discussing problems from week 1 to week 12, some important problems. I'll take one or two problems from each week, and we'll be discussing them at the end. That we term it as a recap session. That will be scheduled on 20th October, again from 3 p.m. to 5 p.m. I think the confirmation mail regarding that will be sent to you after, I think, live session 12 is done. And other than that, since the role is pretty small now towards the end of the live sessions, you guys can always ask your doubts by unlocking your microphones, or you can type in the chat box whatever is feasible to you guys. Also, due to bandwidth issues, as I'm not currently in the campus, so I have disabled my camera. Sorry for that, but I think that doesn't matter. We can proceed without that as well. So this is week 11, and we'll be discussing problems that are related to week 11 material, that is mainly microprocessor 8085, and also week 12 is also based on microprocessor 8085. So without further ado, I think we can start. So before proceeding to the live problems for today's live session, we'll discuss something that is known as architecture of 8085. I'll just briefly go over some of the points or some of the functionalities of 8085 architecture. So this week I have kept this slide for architecture of 8085. Next week I have pin diagram. We'll be discussing the pin diagram. That is for the next week. This week I have only taken up the architecture, and here I will discuss some of the functional units. Just a brief overview. I won't dive down in deep. I won't dive deep into the functionalities because that's not the what we are supposed to do here. We are supposed to solve only the problems. But just to give a flavor of it, since I think I deem it to be important, I kept it as here. So architecture is something that you guys should be familiar with. So we can discuss the architecture, just an overview. You can say just walk through it. So this is a architecture of 8085, and 8085, as you all know, is a 8-bit general microprocessor, right? This here is your architecture, this complete thing that you see on the slide. So this 8085, it has following functional units, right? So first we'll start with ALU, or the arithmetic logic unit, here also called as ALU. What this ALU does is, it is used to perform mathematical operations like addition, multiplication, subtraction, division, and also operations like decrement, increment. Also, this ALU performs logical operation, bit shift operations, and arithmetic operations. So what I will again repeat, this ALU, or the arithmetic logic unit, is used to perform mathematical operations like addition, subtraction, multiplication, division, decrement as increment as well, and also logical operations like bit shift operations, arithmetic operations, and bit shift operations. Now, after that, the other functional unit that we have here is flag register, right? So it is a 8-bit register. Flag, it's a 8-bit register that stores 0 or 1 depending on the value stored in the accumulator. So the contents of the flag register are 0 or 1 depending upon the value stored in the accumulator. Among these 8 bits, 5 bits are important, 3 are don't care. So it is a 8 bit, but among these 8 bits, 5 are important, 3 are don't care. After that, we have accumulator. This accumulator is also an 8-bit register. So this accumulator is also used an 8-bit register is used to program input output arithmetic and logical operations. It is connected to the arithmetic logic unit and the internal data bus. It is also termed as the heart of the microprocessor. So this I'll write here, accumulator, also termed as heart of the microprocessor. So why it's termed heart of the microprocessor? Because for all arithmetic operations, accumulator's 8-bit pin will always be available and will always be connected to the ALU. So I'll again repeat, because for all arithmetic operations, accumulator's 8-bit pin will always be connected with the ALU. So this was, what should I say, accumulator. Now, so far we have discussed the arithmetic logic unit, that is ALU, and we also discussed the flag register. Now accumulator is also done. Now we have general purpose register. So where are the general purpose register? These are here. The general purpose register, there are 6 general purpose registers. These register can hold 8-bit values. These 6 general bit registers are B, C, D, E, H and L. B, C, D, H and L. And also there are 2 reserved registers which are termed as W and Z. After that, we have the program counter, which comes under the CPU section, and the program counter holds the address value of the memory to the next instruction that is to be executed. So this program counter holds the address value of the memory instruction to the next instruction that is to be executed. After that, we have the timing and control unit. It comes under the CPU section, and it controls the flow of data from the CPU to the other device. After that, we have the interrupt control. There are 5 interrupt signals in 8085. These are trap, reset 7.5, reset 5.5, reset 6.5, and INTR. And the priority of these interrupt signal is trap is greater than reset 7.5 is greater than reset 6.5 is greater than reset 5.5 is greater than INTR. And what this interrupt is basically means, I have main program that is being executed. I have this interrupt signal. This main program stops. Then next instruction is executed, and then the main in program is executed again. After that, we have the data slash address bus. So we have here data bus, and here we have the address bus. So the data bus is bidirectional. So from this arrow, you can see this is bidirectional and carries data which is to be stored, right? And we have the address bus, which is unidirectional, and it carries a location where data is to be stored, right? So this was just a brief overview of the architecture of 8085. So let me write architecture 8085. I thought we'll have it before we proceed to our live problems session. And in the next week, where we'll also discussing problems related to 8085, we'll have the pin diagram of this 8085. We'll discuss that briefly. I didn't dwell deep into the details of 8085. Just I wanted to give a brief overview. Now let's just start with the first question of today's live session. It states that how many flags are there in 8085 microprocessor? I think I already said it in the arc while discussing the architecture. Yeah. So one of the students has written. Anyone else? As rightly pointed out, option B, that is 5. Option B, that is 5, is the correct answer. Just give me a brief moment. I need to write down the attendance of today's live session. So 6, yeah. So as rightly pointed out by the one of the participant, option B is the correct answer. So as I told you, this flag register there were is of 8 bits, right? 5 are important, 3 are redundant. And the value of these 5 is based on the contents of accumulator, right? So I have this D7, D6, D5, D4. So these are my 8 bits of the flag. So what are these 5 flags? Number 1 is the 0 flag. Number 2 is the carry flag. Number 3 is the sign flag. Number 4 is the parity flag. And number 5 is auxiliary carry. So can anyone tell me when is 0 flag 1 and when it's 0? When is 0 flag 1? When will be 0 flag equal to 1? Yes, when the accumulator content is 0. So it will be 1 when accumulator is 0 and 0 else. So I'll again repeat, 0 flag will be turned on when the contents of the accumulator is 0, and it will be 0 when the content is non-zero. Now this was the 0 flag. Now the carry flag is 1 when after the arithmetic operation carry flag is 1 when after the arithmetic operation result is more than 8 bits, right? Carry is 1, else carry is 0. So this was the carry flag. Now sign flag, when sign flag is 1. Can anyone tell me when the sign flag is 1? Yes, when the number is negative and it's 0 and it's positive. So this was sign flag. Now what about parity flag? When it's 1? Yes, for even parity it's 1 and for odd it's 0. Now auxiliary carry. Can anyone tell me about auxiliary carry? When it's 1? When is auxiliary carry 1? Yes. So this auxiliary carry is used in BCD addition and is 1 when there is carry transfer from D3 bit to D4. That is exactly what you said, when there is a generation 4-bit carry is generated. Now at the start I made this 8-bit representation. So here at each position we will fill the flags. So at bit position D7 we have the sign flag, at D6 we have the 0 flag, At D4 we have the auxiliary carry, so AC, let me call it AC. At D2 we have the parity flag, and at D0 we have the carry flag. So all others are don't care. So this was about question number one, which asked us how many flags are there in 8085 microprocessor. The answer to that was five. We have the A5 flag of 8-bit register, three are redundant, five are important, and we discussed each one of them. Now, question number two, I think I discussed this in the architecture. I would like you guys to answer. So the program counter stores a address to the current instruction executing by the processor. Option B, address of the previous instruction executed by the processor. Option C, address of the next instruction to be fetched from the memory. Option D, none of the above. So the students, can you please answer what is the correct answer to this question? Just write the correct option only. No need to write the complete answer. Oh, I have one of the participants that answered. Anyone else? C. It's option C, as rightly pointed out by most of you guys. Address of the next instruction. Address of the next instruction to be fetched from the memory. So now question three. I think there was supposed to be one question. Uh, okay, yeah. So question three. Actually, I had kept one question, but I checked the contents of this week, so it was overlapping. So maybe at the end we'll discuss something. Till then, just omit it for now. Let's just discuss question 4 right now. So the question asks us, which of the following flag is not affected by CMP and CPI instruction? Anyone? Which of the following flag is not affected by CMP CMPI instruction? Which of the following flag is not affected by CPI instruction? CMP CPI instruction. So basically CMP CPI instruction is basically compare instruction. So when we talk about the CMP instruction, it is a 1 byte instruction, right? So CMP R/M, where R is for register, M is for memory with accumulator. So it is a 1 byte instruction, as I already told. It compares the data byte. It compares the data byte in the register or memory with the contents of the accumulator, right? So 1 byte instruction used for the comparison of data byte in the register or memory with the contents of the accumulator. So number one, now if A, so by A I mean accumulator, contents of accumulator is less than the contents of register or memory, then carry flag is set and zero flag is reset. Number two, if A equals to register slash memory, that contents of memory, then zero flag is set and carry flag is reset. Number 3, if A is greater than R slash M, the carry flag and zero flag are reset. So these are the three conditions. When A is less than Rm, carry flag is set, zero flag is reset. When A equals Rm, zero flag is set, carry flag is reset. When A is greater than Rm, carry flag and zero flag are reset. When memory is an operand, its address is specified by the HL pair. No contents are modified. However, all remaining flags, that is sign, parity, and auxiliary carry, are affected according to the result of subtraction. Right. So what I meant to say is, so we saw that sign flag is not affected by this. So what we saw is when the memory is operand, its address is specified by HL pair. No contents are modified. However, all remaining flags are affected according to the result of subtraction. So the only thing that is not affected by this is the parity flag. Now we can move to this question. So the question is, find the total delay produced by the following program. So we are given this program and we need to find out the total delay. So let's just write the first line of the program, that is move immediate C 0E hex. So this is move immediate C. So contents of C will be loaded by 0E hex. So 0E hex is how much? Is 14 in decimal, right? Now this is the first instruction. Can anyone tell me how many T states does this instruction take? Anyone else? So as rightly pointed out, it takes 70 states. Then I have loop DCR. What does DCR stand for? Decrement C. And how many states it takes? Correct. And then we have J and Z. What does J and Z mean? JN. There is N. It is jump on non-zero, not on zero. So when it's non-zero, it will go here. And how many states it takes? How many states it takes? 10T. Anything else? Is it only 10 or there is some condition associated to it? Yes, 10 and 10 minus 3, that is 70 when condition is not met, right? So this was with the states thing. So now we'll find the total, how many total T states it takes. So that is equal to T outside the loop plus T inside the loop. So t outside the loop is just this much, that is equal to 7, and t inside the loop. So this will stop counter when these 14 states are counted. So it's 14 multiplied by total states is 10 plus 4, 14. 14 cross 14. 14 is from the count and 14 is the states inside the loop. Do I need to subtract anything? I think answer is already written in the chat. Yeah, minus 3. Right. So I'll subtract 3. So 14 square is 196 minus 3 is 193. So total state t states will be 7 plus 193, that is 200. And time period, since clock is equal to 8 megahertz, time period is equal to 1 by f is equal to 1 by 8 into 10 to the power 6. So total time will be equal to 200 multiplied by 1 by f, that is 200 multiplied by 1 by 8 into 10 to the power 6. How much is it? Can anyone tell me? Can anyone do the maths for me? Yes, 25. And the units? And the units are microsecond. Thank you so much. So 25 microsecond. Now this is another kind of theoretical question. Can you guys tell me how many T states are required to execute the following instruction? LXID 2589 hex. Correct. By the way, what does this LXID mean? Load. Yes. LXI means load. It is an instruction of loading a 16-bit data into a specified RP. What is RP? Can anyone tell me? This is a mnemonic for something. What does RP mean? It means register pair. And what is the register pair you specified here? In the given instruction. No, no, not CD. Not CD. D and D and not H. Now tell me, what is it? D and yes, correct. D and E. So this was question number 6 of today's live session. Now we have question number 7. So we have this question. In the following 8085 assembly language program, assume that the carry flag is initially reset. What is the content of accumulator after the execution of the program? So we'll be performing individual steps, and then after the execution of the program, we'll see what will be the contents of accumulator. So first thing we have is MVIA 04 hex. So that means content of accumulator get loaded by 004 hex, that is 0000100. So this is the contents of accumulator and my carry flag is reset. So basically, the T states are dependent on internal clock pulse. So you have to look at the literature where they're only shown. You can refer to the literature to see how many T states individual operation take. You need to check but it depends on the internal clock of the microprocessor. So usually some instructions take 4, some take 7, some take 10. You need to they will be given, they will be definitely given, but what for the I think for some of them you should remember. Yeah, for I think for exams you need to memorize. I think you can refer to the chart, you can memorize them. You can memorize them, it's not a big deal. You need to memorize them, that's my suggestion. Yeah, you need to memorize it. You can refer to this book, I think Gonkar. Have you guys gone through that book? That is a very good, really good book for microprocessor 885. You guys should refer it. Actually, we used to have course, at least in my BTech days, when I did my BTech back in 2016. So we used to refer Gonkar. We used to have a separate course on microprocessor 885. So you can refer to that book and get these values and memorize them. And I think maybe in lectures you will have all the values. So nothing will be asked outside the lectures. So this is move immediate and we have the contents of accumulator as 04. Now after that is RRC. Can anyone tell me what is this instruction? RRC? Anyone? Does anyone know? Right shift, yeah. So the complete name is rotate right accumulator. So when we do the right shift in binary, what does that mean? When we do the right shift, what does that mean? Right shift when we do in binary, simply divide by 2 operation. So we'll just right shift the entire thing. So it will be 0, it will be 0 0 0 0 0 1 0, and carry is also 0. Now move BA. So the contents of A will move to B. So B will be equal to 0 0 0 0 0 0 1 0. So that is 02 hex, carry 0. And then we have RLC, that is left shift. So what will be left shifted? Contents of the accumulator. So left shifted, it will again become 0 0 0 0 0 1 0. So this will be 04 hex. Then I have again RLC, again left shift. So I'll have 0 0 0 1 0 0 0. So it will be 08 hex, right? Then this is done, this is done, this is done, this is done. I have add B. So add B. What does this mean? Adding the contents of B to the accumulator. So A is accumulator is 0 0 0. Sorry, B is, what was B? B was 0 2. Yeah, B was 0 2, and we are adding it to the contents of accumulator, which is 8. So 8 plus 4 is simply 12. So it will be 0 0 0 0 1 0 1 0 1 0. So it is no, 8 plus 2 is 10. Sorry, 8 plus 2 is 10. So it will be 08 0a hex, right? And after that I have the final operation, that is RRC. So it will be 0 0 0 0 0 0 0, then it will be 0 1 0 1. So this was 10. 10 divided by 2 is 5 simply, if you want to save time, but I need to go over each step, so it will be 0 5 hex. So after all the operations, the contents of accumulator will be 0 5 hex. That is option A. I think you forgot the last instruction, right? I hope you got it. Now, this was question number 7 of today's live session. Now I'll go over to question number 8. I would like you guys to solve it first, then I'll show you the solution. So I'll just give you a couple of minutes, maybe more, 3 minutes. That is sufficient for this problem. So I'll read the question for you guys. What are the contents of accumulator after the following program is executed? LXI B0400, loop DCRB, move AC ORAB, and jump on non-zero loop. By the way, one instruction we haven't so far encountered. Do you know what this instruction means? Please tell me what this instruction means, and then you can proceed with the question. Yes, this is OR operation of B with the content of accumulator A. Yes, the correct answer is option D. So let's just see how it's done. So we have first LXI B 0400. That means B gets loaded with 04 and C gets loaded with 00. Then I have DCRB, that is a decrement condition. So what I will have here is DCRB move. Let me just write this thing here. I'll have DCRB move AC OR AB JNZ loop. Here I will have iteration 1. So decrement B in iteration 1, this will become 03 hex. Now the content of C will get loaded to accumulator. So A will be 00 hex since C is 00. Now OR of B with A. So 03 gets OR with 00. So ultimately when you basically whenever you have A OR with 0, it's always A, right? This is a property. So OR of, so it will be 03. Now the contents of accumulator are 03. It's a non-zero. It will go back to this condition and we'll have iteration 2. Once we'll have iteration 2, I'll have decrement operation. So it was 03, now it will have 02. A contents of A will get loaded by C, so that is 00. Again OR of B, so it is 02 again non-zero. So iteration 3, this will be B will be 01 hex. A will be loaded with C, so that will 00. OR of accumulator contents with B, so it will be 01 again non-zero. We'll have iteration 4 where B becomes 00, A is also 00. OR of B will be 00, so it's 0. So ultimately my contents of accumulator, so condition will not be fulfilled, so program will be executed and my contents of accumulator will be now 00. That is option D, as rightly done by one of the students. I think all others will have also done it, but they didn't write the answer. Anyways, now I'll have again a question for you guys. This is a simple question. You guys can type in your answer. Which of the following flag is not available in 8085 microprocessor flag register? Anyone? Yes, right answer by you guys. So it's overflow flag. We saw it, sign, zero, and carry flag. Even we discussed thoroughly in this question number 1 as well. So now question number 4. The accumulator contains 0 FB hex and B contains 12 hex. What are the contents of A and B after the given instruction is executed? So A is your accumulator and B is your register, general purpose register. So instruction is ORAB, that is OR operation between accumulator container and B. So B gets loaded with 12 hex. A gets loaded with FP hex. So A is your 1111, B is your 10, B is your 11. I think 8 plus 2 plus 1, 1 0 1 1, right? So B is your 1 2. So 0 0 0 1 0 0 1 0, and you have OR operation between them. So it's 1 1 0 1 1 0 1 1. So this is your result of the operation that gets stored in where it gets stored in accumulator, and it's your F and this is your B. So my accumulator is FP after the operation. What about B? B remains unchanged. B is 1 2 x. So its A is FB, B is 1 2. Option B. Now I have this question, that is question number 11 of today's live session, which states that what are the contents of the accumulator after the following instructions are executed. So we have 3 instructions written and we need to find out what are the contents after the following instructions are executed. First one is MOVA12 hex. So accumulator gets 00010010 loaded, right? Then I have CPLA. Anyone? What does this CPL mean? Anyone, what does this CPL mean in terms of instruction? What we have to do? What does CPLA mean? CPLA simply means complementing the contents of accumulator. So now it will become 100. If we complement it, it will be 110 1101. So complement and then add a. So what we have to add to a? 0 and x. So we have to add 1 to it. 110 1101, adding 1. So it will be 110 110 111. So it is 8 plus 4. So this is 8 plus 4. Yeah, this is E hex. That is option A. Sorry, option B. Contents of accumulator is this. Anyone can tell me what is the complete operation? This thing. Ultimately, these three lines of code, what it does, we have a specific name to it. What is the operation known as? Yes, two's complement. Thank you so much. So this is the two's complement that it does. So this was question number 11. Then I have a question for you guys. Can you tell me which of the following instruction is an example of implied addressing mode? Which of the following instruction is an example of implied addressing mode? So I think some of you have written the correct answer. It's option A, that is CMA. So the CMA is here, complement the contents of accumulator. So what is this implied addressing mode? So implied addressing mode is a mode in which no operand is specified in the instruction. So implied addressing mode is no operand is specified in the instruction. Data is itself present in the instruction. For example, RRC, RLC. So this was a pretty simple question. Now we have question number 13 of today's live session. It states that what are the contents of register B after the following instruction are executed? MVIB FFX, MVIC FFX, INXB. So can you guys solve it? I'll just give you a couple of minutes and you guys can write your correct answer. Anyone else? Has anyone else done it? If so, please write down your answers. So let me just show you the. So MVI B gets loaded with FFX, that is 1 1 1 1 1 1 1 1. C gets loaded with FFX, that is 1 1 1 1 1 1 1. Just a second, I think there is some issue with the presentation. Yeah, we were here. So B gets FFX, so it's 1 1 1 1 1 1 1 1. C gets FFX, that is 1 1 1 1 1 1 1 1. And INXB, that is the increment operation where the contents of register pair are increased as one entity. That means if you increase 1 1 1 1 1 1 by 1, ultimately it becomes 0 0 0 0 0 0 0 0. So it's 0 0 hex. Option B. Now I have this question. This is kind of a follow up from the last week's lecture. So consider the following VHDL code. What does it represent? Process begin, clock gets assigned 0, wait for 20 seconds, clock gets assigned 1, wait for 12 nanoseconds, add process. Can anyone tell me what it is? Think again. I think you got slightly confused. Think again. So answer to this is option 2. So we have process and there is nothing in the sensitivity list. That means it's a never ending process. So we have clock gets assigned to 0 and wait for 20 nanoseconds. So clock gets assigned to 0 will wait for 20 nanoseconds. Then clock gets assigned 1 and will wait for 12 nanoseconds, and it will repeat again and again. So this is 12 and this is 20. So on time is 12 nanoseconds, off time is 20 nanoseconds, right? So option 2 is the correct answer. I think we have seen it in the previous question as well. How many T states are required to move for move AC instruction? That is, how many T states required to execute move AC instruction? Anyone? I think you should be knowing this by now. Anyone? How many t-shirts? So the number of t-shirts required for this instruction is A, option A, 4. Now I have another question for you guys. So what happens to the contents of stack pointer after push instruction is executed? Option A, contents of stack pointer decremented by 1. Option B, contents of stack pointer decremented by 2. Option C, contents of stack pointer incremented by 1. Option D, contents of stack pointer incremented by 2. Anyone? What is the correct answer? So the correct answer to this is contents of stack pointer gets decremented by 2 by push instruction. Now I have this question. I would like you guys to solve it first, then I'll show the solution. The following 5 instructions are executed on an 885 microprocessor. The contents of accumulator immediately after the execution of the fifth instruction is. So you have these instructions and you need to find out what are the contents of the accumulator after the execution. So one of the students has solved it. Let's just wait for one more minute and then I'll show the solution. So let me just show you the solution. We have this first instruction MVI A65X, that is A gets loaded with 011 and then MVI B gets loaded with 12 hex, that is B gets 0001 0010. Then you have add B, so contents of B gets added to accumulator, so it's A plus B. So what will be that? 1 1 1 0 1 1 1 0. Right, so this is 77x, so A is now 77x. Then I have CMA, that is complement of contents of accumulator, so it will be 1, so it will be 1000. I am complementing this thing, 10001000. So that is 88 hex. Now ANI 68 hex. This is the AND operation of 68 with A. So AND of 68. 68 is 0 1 1 0, 8 is 1 0 0, and its AND operation I need to do with 88 hex. So 68 88 1 0 0 0 1 0. So its AND operation will be 0 0 0 1 0 0 0 0. So am I missing something? No, it's correct. So it will be 08 hex. That is option A, as rightly pointed out by you guys. Then I have this question. So what is the total delay given by the program? Assume 8085, what did I say? Assume 8085 operates with 5 megahertz clock. Can you guys do it? I'll just wait for a couple of minutes. It should not take more than that. Do it and then I'll show the solution. Has anyone done it? So let me just show you the solution. This is question 18. Yeah. So LXIB gets 0 1 2 3 hex. So B gets loaded with 0 1, C gets loaded with 0 2 3 hex. Then I have loop, and this takes 20 states. Loop decrement dxb 60. So it will decrease the content of B. Then move AC 40. So C, content of C get loaded in A. ORAB 40 and jump on 0 loop 10T, and it's 70 when the condition is not met. So T is total is T outside loop plus T inside loop, and T outside loop is 10. T inside loop is 6 plus 4 is 10, 10 plus 4 is 14, 14 plus 10 is 24. B B is how much? So yeah, so this is 123 hex. So 123 hex, when you do 123 hex in decimal, it becomes 291. You can do the math, so it's 291. So time inside the loop will be 24 into 291 minus 3. So total will be 10 plus 24 multiplied 291 minus 3. So this is 10 plus, I think this thing is, complete thing is 6981, 6991. This is complete thing is 6981. So total will be 6991, and time will be 6991 multiplied by 1 by f. So it's 6991 multiplied by 1 by 5 into 10 to the power 6. So this thing is equal to 1398.2 microsecond and also 1.3982 milliseconds. So option A and option C both are correct. So typically you won't have multiple answers. It was one of the, actually when I was doing the coursework, when I was doing this TA work in back in 2022, this type of question was asked in assignment, I think. So I think it's by mistake that both the answers are correct. Typically you will have only one option correct, that is correct. Now I have another question, that is question number 19. What what is the accumulator content after the execution of the following instructions? So A gets 5 5, that is 0 1 0 1 0 1 0 1. RLC is, that is rotate left, so it is 1 0 1 0 1 0 1 0. So basically I took the sum of these things, 6 plus 4 plus 4 plus 10, and I know one thing for a fact, that it will be uh, loop will execute for this thing in decimal, that is 291 times, and for the last state only 70 states will be taken. So that's why I have written minus 3 here. Why I have written it will be executed for 291 times? Because if you look carefully in this operation, it will be executed only when the contents of B will be equal to 0, right? So this will be executed how many times? What should I say? 1 2 3 x times, because dxb means you have to decrease the contents of BC register, right? So first C will get decreased, then B will get decreased, so it will be executed 291 times, that I mean to say, because this OR of B will always be non-zero unless B will turn 0, right? So that's how I arrived at this conclusion. 291 time 291 multiplied by 24 was the sum of these, minus 3, because at the last time condition is not met, only 70 states are required. So that's why this minus 3 came here. T outside the loop was 10. So 6981 plus 10 is 6991. Then I multiplied it by the time period of the clock. So I got the answer. I think we also did this type of question here as well. Here we can refer to that as well. So we were discussing this question now, 19. So A is 5 5, that is 0 1 0 1 0 1 0 1. Then RLC also will left shift each bit by one, to left shift it, so it becomes 1 0 1 0 1 0 1 0. Then again I will have RLC, it will become 0 1 0 1 0 1 0 1. Then again RLC, it will become 1 0 1 0. So this is A, this is A, so it is AA hex. Option B. So it's 90. Now question Now question, what happened? I think I'm facing some bandwidth issues right now. So this was, I think, 19 we did last. Now I have to do 20. Just a second, I'll reopen it. It's having some issues. So 19, 21, 22. Yeah. So now we have 20, question number 20. What are the contents of BC register pair after the following instruction is executed? LXI, B, ABCD, hex. So that means B gets loaded with AB, C gets loaded with CD hex. So A, B, option C is correct. Now question 21, we have what is the content of accumulator after the following program is executed. Assume 885 register is flag register is initially reset. So I have MVI A F2 hex. So A gets loaded with 1111 0010. Then RRC. So right shifting it. So it will be 01111001. So now it will be after RRC it will be, how much is it? So it's 7 and 9, 7 9 hex, right? Then I have move BA. So contents of A will be moved to B, so B will be 7 9 hex. Then I have RAL. RAL is basically rotate through accumulator left. So we have something like the D7, D6, D5, D4, D3, D2, D1, D0, and we have here carry. So everything will be left shifted by one position, and D7 will go here and carry will go here. So initially carry was equal to 0. So RAL, so it will be 1 1 1 1 0 0 1, and it will be 0, and carry will also be 0. Then I have again RAL. So now again left shifting, so it will be 1 1 1 0 0 1 0 0, but now carry will be equal to 1. Now I have add B. So add B. B was 7 9 here. So I write 7 here, 0 1 1 1 1 0 0 1, and I have addition operation, so it will be 1 0 1 1 1 0 1 plus 1 is 1 1 is 0, and carry will be 1. So this much is A is equal to what, 0 1 0 1 1 1 0 1. So that is 4 plus 1 is 5 5 5 5D, right? And finally I have RAR. Same thing, but operation will go right this. Just a second, I need to attend this one call. Sorry about that. So sorry about that. Actually, it was some important call. So we can resume. So now we have the contents of accumulator, that is 5D. By the way, am I audible? Can someone confirm? Actually, I had turned off the microphone. Yeah. So contents of the accumulator were 5D. Now I have to do RAR, that is a right rotate through accumulator right. So that is operation will be like this, and this will go here and carry will go here. So I'll do the right shift operation and carry flag was 1. So my ultimate answer will be 10101110. That is A A E hex. That is option A, as rightly done by one of the students. And now the last question of today's live session. Which of the following register is not a general purpose register? Anyone? Which of the following is not a general purpose register? I think it can get confused. It will be confusing. So correct answer is accumulator. That is option D. So that was all for today's live session. We'll meet next week from 3 p.m. to 5 p.m. and where we'll be discussing week 12 related questions. That is also based on microprocessor. So thank you guys for joining. See you next week.